Here's a really cool integral. I find it really cool because although it looks tame in comparison to the integrals, the crazy sort of integrals we normally do here on Maths 505, there's a nice surprise within its solution development. So this is going to be a very nice integral to evaluate. As always, we refer to the integral as I. And the reason I say it's more tame is because if I write this as the integral from 0 to pi by 2 of x cubed times the squared cosecant of x dx, then I have a nice integration by parts structure here, because the antiderivative of the squared cosecant is the negative cotangent of x. So this implies on integration by parts, we have negative x cubed times the cotangent of x, with the limits being 0 and pi by 2. The two negatives canceling out, you have the integral from 0 to pi by 2 of the derivative of x cubed, which is 3x squared, times the cotangent of x dx. And you can verify in the limit as x approaches pi by 2, because the cotangent equals cosine by sine, so that approaches 0. You can verify in the limit as x approaches 0, that is, using L'Hopital's rule, that this term here collapses to 0. So it's 0 in both limits, and we can just cross this out. And this implies that I equals 3 times the integral from 0 to pi by 2 of x squared times the cotangent of x dx. And again, you have a nice integration by parts structure. So on integration by parts, you have 3 times x squared times the antiderivative of the cotangent function is log sine x, where the limits are 0 and pi by 2, minus 3 times the integral from 0 to pi by 2. The derivative of x squared is 2x. So instead of writing a 3 here, I have 3 times 2, which is 6, times x times the logarithm of sine x dx. Again, in the limit as x approaches pi by 2, you have log of 1, which is 0. And for the limit as x approaches 0, again, you can use L'Hopital's rule and just cross this out completely because it evaluates to 0. So this implies that I equals negative 6 times the integral from 0 to pi by 2 of x times the logarithm of sine x dx. Now this integral is really nice. It's really nice because log sine x doesn't have a nice antiderivative. So we can't do another integration by parts, and we'll have to come up with some other line of attack. And you all know how much I love infinite series expansions, and there's one infinite series in particular that I've grown very fond of over the past few months. And that's the series expansion for log 2 sine x that can be derived using basic complex analysis. All you need is the definition of the sine function from complex analysis, and from there you can work your way towards the series expansion. Link in the description below for my video proving that log 2 sine x can be expanded as the negative of the sum over the positive integers k of the cosine of 2kx divided by k. And this implies that log sine x equals negative log 2 minus the sum over k of the cosine of 2kx divided by k. So for integration purposes, all I have to do is multiply everything by x and integrate from 0 to pi by 2 and multiply by 6 to get the target integral I. So this implies that I equals negative 6 times integral 0 to pi by 2 negative x times log 2 dx minus the integral from 0 to pi by 2 of the sum over k of x times the cosine of 2kx divided by k dx. The first integration is pretty straightforward. We have negative 6 times on integration x squared by, oh, terribly sorry about that. There's a negative sign as well. So negative x squared by 2 times log 2 with the limits being 0 and pi by 2. So this sorts out to negative pi squared by 8, correct? Yeah, that's about it. Minus, when you switch up the order of the summation and the integration operators, you have the sum over k of the integrals from 0 to pi by 2 of x times the cosine of 2kx divided by k dx. And because the factor of 1 by k is independent of the x variable with respect to which we're integrating, we can just pop this outside the integration operator. And the resulting integral needs another dose of integration by parts. So let me just take this to the side as I sub 1, defined as the integral from 0 to pi by 2 of x times the cosine of 2kx dx. And all we need is one integration by parts here. So we have x times sine 2kx divided by 2k, with the limits being 0 and pi by 2. And as x approaches pi by 2, we have sine of k times pi. K being a positive integer means that this term is always 0, and for the 0 limit, again, you have a 0 because of the x and the sine term. Okay, minus 1 by 2k times the integral from 0 to pi by 2 of cosine, oh, sorry about that, we integrated to get a sine of 2kx dx, and the derivative of x is 1, of course. On integration once more, we have another negative sign, so that's 1 by 4k squared now, times the cosine of 2kx, the limits being 0 and pi by 2. So we have 1 by 4k squared times negative 1 to the k minus 1, because cosine of k times pi is negative 1 to the k, of course. Okay, cool. So that's I sub 1 for you. And back to the original integral, that had a negative 6 times a negative pi squared by 8 times log 2 minus the sum over k of 1 by k times this integration result. So you have a 1 by 4k cubed times negative 1 to the k minus 1. Okay, let me get rid of the brackets over here. Just looked unnecessarily weird. And here, notice one thing, that if k is some even integer, then you have 1 minus 1, which is 0. So the only values of k we're interested in are values of k of this form, 2n plus 1, where n needs to be a non-negative integer. Notice, non-negative. We have to include n equals 0 to include k equals 1. So this implies I equals, on multiplication, 3 pi squared by 4 times log 2. Again, the two negatives canceling out. You have 6 by 4 times, this here will give you negative 2 for odd values of k. So 6 by 4 times negative 2 sorts out to negative 3, correct? So you have minus 3 times the sum over the non-negative integers n of 1 by 2n plus 1 cubed, which is, of course, related to Apéry's constant, or zeta 3, that is. So zeta 3 equals the sum over n of 1 by n cubed. So if you decompose this into even and odd integers, then you get the sum over n of 1 by 2n cubed plus the sum over n of 1 by 2n plus 1 cubed, which is the required sum. So notice something here, that you can write this as 1 by 8 times exactly zeta 3. So this implies that the sum over the non-negative integers n of 1 by 2n plus 1 cubed equals exactly 7/8 of zeta 3. So finally, we have a very aesthetically pleasing result indeed, that I equals 3 pi squared divided by 4 times log 2 minus 3 times 7/8 of zeta 3. And of course, you can factor out a 3 by 8 here. So you can write this as 3 by 8 times 2 pi squared log 2, or pi squared log 4, minus 7 times Apéry's constant. A beautiful result indeed for a surprisingly nice integral. And I hope you enjoyed the video. Be sure to like and subscribe. Thank you. See you next time.